Good evening. Thank you all for coming. We're quite pleased to see this attendance given yesterday's postponement of the lecture. I hope you had a much more pleasant trip into town today than you would have had yesterday. My name is Rick Carlson. I'm the director of the Department of Terrestrial Magnetism. That's one of 6 of the research departments of the Carnegie Institution of Washington. Over the last 20 years, the field of planetary sciences has grown from consideration of the 8 planets in our solar system to the discovery that the majority of stars in the night sky actually have planetary systems of their own surrounding them. Ground and satellite-based planet-finding missions have found literally thousands of planets orbiting stars in our galaxy. Besides the mere fact that these planets exist, a major surprise has been how different the individual planetary systems are compared to our own. Our speaker tonight, Scott Sheppard, an astronomer at Carnegie's Department of Terrestrial Magnetism up in upper northwest Washington, is one of the people whose work might explain why our solar system looks the way that it does. As an astronomer and with an expertise in the outer edges of our own solar system, he's discovered numerous moons, active asteroids, and dwarf planets. In fact, you might remember the excitement he created last summer when he announced the discovery of 12 new moons of Jupiter. But the biggest game changer happened in 2014 when Scott and his collaborator Chad Trujillo redefined the edge of our solar system with the discovery of 2012 VP113. These are the names you have to enjoy with outer planet objects. But they nicknamed it Biden after the then vice president. It's been more than a decade since the previous discovery of a large object in the outer solar system, the minor planet Sedna. So the discovery of a second such body allowed scientists to start making connections between the two. When Sheppard and Trujillo announced their discovery of Biden, they also noted similarities in the orbits of both Biden and Sedna, and then subsequently a few other distant objects that suggested that they were being controlled by a planet perhaps even bigger than our own Earth that was lurking out there somewhere past Pluto and controlling the orbits of these distant planets. Although Sheppard and his team were the first to propose a 9th major planet on the fringes of the solar system, their suggestion was like a starter's pistol, and many others jumped into the hunt. Currently, Sheppard and his team, which includes David Tholen, are conducting the largest and deepest ever survey attempted in our solar system's fringes. The objects they discover are like breadcrumbs that are leading them to planet X and to a better understanding of our own solar system's history. Sheppard had received his bachelor's degree in physics from Oberlin College and his PhD in astronomy from the University of Hawaii. He joined Carnegie as a recipient of the prestigious Hubble Fellowship in 2004, and then became a staff scientist in the department in 2007. If the Guinness Book of World Records hold a record for the discovery of the most moons, Scott Sheppard would own it. He is also the lead discoverer of the most distant solar system object ever, 2018 VG18, that they've nicknamed Far Out. As you'll see, this is a problem in nomenclature because when you discover something even farther out, it becomes far, far out. Tonight, he's here to talk up to us about the exciting work on the solar system's outer edges and the possibility of an undiscovered planet lurking out there. So ladies and gentlemen, please join me in welcoming Scott Sheppard.
Thanks. Yeah, thank you for that introduction. And yeah, what a difference a day makes, right? All that snow is pretty much gone. And I kind of wanted to start out basically with this picture here. And this is not the snow we saw yesterday. This is actually on Mauna Kea in Hawaii, where I was last week observing. And we had a snowstorm. And so we weren't able to actually open the telescope. And this storm basically followed me all the way back here to DC. So it's been following me. And I have not been having good weather in the last week. So hopefully things will improve. That's me standing a few feet of snow in front of the Subaru telescope there in Hawaii. And it looks really good when you're at the beach and you can look up, you can see the snow-capped mountain there in Hawaii. So it's a very beautiful sight, except when you're up in it. So I actually had another name for this talk, why your horoscope has been wrong all these years. And that's, if there's this planet out there, everything will be messed up. So hopefully we'll find it and get everything right. So this is an image I always like to show. It basically shows the Magellan Telescope. So these are 6.5 meter telescopes down in Chile, which Carnegie is majority owner of. And these are the telescopes that I use a lot to do a lot of the observations. So this is the southern hemisphere, and this is a real picture taken about 30 seconds in time. And you can see the beautiful Milky Way galaxy over the telescopes. And you can also see the Magellanic Clouds. So there's 2 satellite galaxies to our galaxy that you can only see in the southern hemisphere. can see it there and there. So it's definitely, if you visit the southern hemisphere, you need to get to a dark site to be able to see the very beautiful Milky Way. You can see it in the north as well, but in the north, it's not as prominent as in the south. And the reasoning for that is our sun, which is about halfway to 2/3 of the way out of the galaxy. When you're in the southern hemisphere, you're looking into the center of the galaxy, whereas when you're in the northern hemisphere, you're looking out away from the center of the galaxy. So the southern hemisphere is a very beautiful site to go out to find a dark observing place. So this slide is to get some of the nomenclature out of the way that I'll be given in this talk. The main thing is that our solar system is kind of divided into 3 main groups. So the inner group, which we call the first domain, has the rocky terrestrial planets, Mercury, Venus, Earth, Mars, and the main asteroid belt. And a unit I'll be using pretty much this whole talk is 1 AU, 1 astronomical unit. And that's simply defined as the distance from the Earth to the Sun. So that's 1 AU. The second domain is what we call a gas giant domain. And you find much bigger planets out there, Jupiter, Saturn, Eris, and Neptune. And the reason these planets are so big is because right here is what we have we call the snow line. Objects interior to that water ice was not able to condense. It was a vapor form, and so the objects didn't form with much water on them. But beyond that, water condenses, so you have a lot of water ice, which is one of the most dominant materials in our solar system. And so these planets were able to gobble all that up and grow really big, really fast. And then our third domain, which is pretty much the focus of this talk, is what we call the icy area. And out here, the volume of space gets really big, the density of material drops off, and so objects have not been able to form into a planet. And it's leftovers from the planet formation sitting out there. And there's several dwarf planets out there, and that's will be the majority of this talk now is things beyond Neptune, which we call trans-Neptunian objects. So if I use the word trans-Neptunian, it just means objects beyond Neptune. A thing to keep in mind is that in our solar system, there's 2 belts of small objects. So there's the main asteroid belt between Mars and Jupiter, and that's dominated by rocky objects. And then there's what we call the Kuiper Belt, which are the objects just beyond Neptune, which Pluto is kind of part of, and that's dominated by icy objects, mostly water ice. And you can actually see this as well. So one of the great things to see as an astronomer is in the morning when the sun starts coming up, you can see what we call the Zydeco Light. So the main asteroid belt has a bunch of asteroids that are constantly colliding with each other, creating dust. And that dust orbits the sun in a kind of a plane. And when the sun is coming up, so the sun is just down here, it reflects off that plane of dust, and you can see this pillar of light. So there's the galaxy I was showing you earlier, and here's the Zydeco Light, a pillar of light of the dust in our solar system, which is another great thing. You need to be very dark adapted to see it, so you need to have like 20 to 30 minutes sitting outside in the dark. So you have to get up well before the sunrise to see it. So going beyond Neptune now, here's a schematic of kind of the outer solar system. We got Jupiter, Saturn, Eris, and Neptune, all on nice circular orbits, kind of nicely spaced. And you got Pluto, which is kind of on a little more elongated orbit. It actually crosses Neptune's orbit. And we now know of over 3,000 objects beyond Neptune in this thing that we call the Kuiper Belt. So we just visited Pluto. The New Horizons spacecraft flew by in 2015, and these are the images we got. So I thought I would talk a little bit about Pluto before we move further out. Pluto is basically dominated by water ice. So it's water ice on Pluto acts kind of like rock does here on Earth. It's so cold out there at Pluto, the ice is so frozen solid that it's the base of Pluto. And there's mountains made of water ice, and on these mountains, so here's a picture showing some mountains on Pluto, and instead of having water ice-capped mountains, the water ice is the mountains, and the snow-capped is methane ice. So all these mountains are covered a lot by methane ice. And there are what we call ice volcanoes or cryovolcanism on Pluto. This is a shot straight down on one of those mountains, and you can see a kind of a caldera hole in the middle of this mountain. And if you do the spectroscopy, look for the elements, you see that it's blue. It's dominated by water ice in there. So we think this is a cryovolcanism. We don't know if it's still occurring now, but in the past, Pluto had ice volcanoes on its surface. Similar to how magma and lava come out of volcanoes here on Earth, Pluto would have ice coming out of its volcanoes. Pluto's moon, Charon, has what I like to call the Grand Canyon. And that has, you can see this massive valley structure here. And we actually believe Charon is just a big ball of water ice. And it was originally, when it formed, it was very hot, so it was probably liquid in form. And then it started freezing over time. And the surface would freeze and out before the interior would. And so that's where you get a crust on the surface. And then the interior would start to freeze. And the one strange thing about water ice is that when it freezes, it expands. Most substances don't expand when they freeze, they actually shrink. But water ice expands, and so we think these vast canyon system was created because the surface froze, and then the inside froze later on and pushed and cracked the surface, and gives us this 7 miles down from the top to the bottom of this canyon. So New Horizons went past Pluto in 2015, and only just last month, it visited one of these Kyber objects. And this is hot off the presses. It's going to take 20 months to get all the data down, so they only have a few of the images back. But this is the object it looked at. So Pluto is pretty big. It's 2,000 or so kilometers in size. This object is only 10 each. It has 2 bilobes, and each one of them is only about 10 to 15 kilometers in size. So this is very, very small object, and it's basically the leftovers of planet formation. Unlike Pluto, which has been heavily processed over time because it's so big, this object is telling us a lot about how probably planet formation occurred. And little objects come together and they form bigger objects over time. And this is kind of a frozen in place formation process where we could see 2 lobes come together, but the density of space is so low out there and the volume of space is so big that they weren't able to accrete anything more than this. So we look forward. It's got to be 20 more months before we get all the data back from New Horizons on this object. So it'll be very interesting times in the next year or two. So moving in terms of discovery of these objects, Pluto was discovered in 1930. It was discovered on photographic plates, and photographic plates are hard to work with. If anyone's ever been to Lowell Observatory in Arizona where they've discovered Pluto, they have the blink, they call it a blink comparator. It's a mechanical device where they took 2 photographic plates that were taken at different times, and they just move them back and forth really fast, and they look for anything that kind of moved. It's very hard to find objects that way, and that's pretty much why Pluto was found and nothing else was known for some 60, 70 years until the 1990s when digital detectors started to be put on telescopes, and they were able to go fainter, and they were able to use the computer powers to start looking for objects. And now we know of over 3,000 objects that are beyond Neptune. So the cameras we use are very similar to the digital cameras you have on your iPhones or your digital cameras, but they're much bigger. The camera that we now use on one of our telescopes is bigger than a small car. So these are massive cameras, some of the largest in the world that we're using to be able to cover big areas of sky. So here's one of those images. This is an image from the Magellan Telescope. This image itself covers about 1 full moon in size. And it's broken up into different parts because they want to read out the image really fast. So they read out the different sections with different amplifiers that we call them. But anyway, if we zoom into just a small thumbprint up there, we get 3 different images. And we image over a few hours to a few days the same part of the sky. And then on this one, we image the same part of the sky 3 times over a few hours. And if you put those 3 images together, you get something like this. So this is a movie of those 3 images. And in this image, you see a lot of stars. So all these circular objects that don't move are background stars. They're stars that are in our galaxy. They're just in the background. There's some elongated objects. These are galaxies. And there's 1 billion stars in each one of these galaxies. So each one of these galaxies has 1 billion stars in so there's that's where you get the word billions and billions from, because there's just so many stars out there. So also in this image is a main belt asteroid, which many people who have a pretty good eye could probably find. It's over here on the left. You can see it goes from there to there to there. And that's a main belt asteroid. It's fairly close to the Earth. It's just beyond Mars. It's actually trailed. We take 5-minute images, so we open up the shutter for 5 minutes to get as much light as possible. And during that time, this object has trailed, and we can see it moving there. Also in this image, though, is a Kyber Belt object. I don't know if anyone's found the Kyber Belt object, but I see some people pointing at it. So up here is a Kyber Belt object. and you can see it moving. It moves much slower, it's much further away, and it's much fainter. Even though this object is hundreds of kilometers in size, and this object's a few kilometers in size, it's much fainter because it's so far away. And of course, we can't look through this data by eye like Clyde Tombaugh did when he found Pluto. We get a terabyte of data a night now when we're at the telescope, so we've written computer programs that go in and find everything that moves and flags it, and then we go in and see if it's real or not. And everything it flags, we check it, and if it looks good, we have to go back to the telescopes a month or 2 months later and re-observe it to confirm it's real. So our main goal starting out in 2010 is we wanted to basically complete the inventory of our solar system. We wanted to find everything that was out in the solar system. And to do that, we actually did not, here's the Magellan telescopes I showed you earlier, 6.5 meter telescopes, some of the largest in the world. We actually started over here. It's a 1.3 meter telescope. It's actually owned by Poland. And they had a new imager they put on it, and it was a fairly wide field. And 1 meter telescopes are easier to get time on, and they have, because of the way optics work, they have bigger fields of view generally. And we were able to cover the southern sky that people have never covered before for basically bright objects, solar system distant objects. And these are some of the discoveries we found. The biggest one we found, the Polish guys named this after a Slavic god, so I will not try to pronounce that. But this is about a third the size of Pluto, and our next biggest one was about a fourth the size of Pluto or so. So we found some pretty large objects out there in this survey, and we basically have now, with 1 meter class telescopes, which 1 meters are about that big, we've covered the whole sky multiple times over with 1 meter class telescopes looking for distant objects. So we found pretty much everything out there that's bright enough for a 1 meter class telescope. What we haven't done is covered the whole sky with next bigger telescopes, 4 meter class telescopes and 6 to 8 meter class telescopes. We have not covered the whole sky to date looking for objects. And this graph is just kind of to show, this is heliocentric distance from the sun. This is a magnitude which astronomers use, but you don't have to understand that scale. The main point here is an Earth-sized object beyond about 200 astronomical units, 200 times the Earth-sun distance, would be too faint for a 1 meter class telescope to detect. So you could have Earth-sized objects or bigger out there that we just haven't found because we haven't covered the whole sky yet with the bigger telescopes. And something I always like to point out is the brightness of an object, the light has to go out from the sun, reflect off the object, and then come back to us. So it's an r to the squared power law out, an r to the squared power law back. That gives you an r to the fourth power law. And what that means is if you move an object twice as far away, it gets 16 times fainter. So things get very faint very fast, even very big objects, Earth-sized objects. This is a list of the current known bigger objects in the outer solar system. And this is mostly to show you that Pluto is shown here, is similar, it's actually smaller than our Earth's moon. Our Earth's moon is bigger than Pluto. Here's the largest main belt asteroid series, but the main point of this plot is to show that there's not just 1 or 2 big objects out there and then a bunch of smaller ones. There's a lot of big objects out there, and Pluto just happens to be on the top of that size distribution. So here's Pluto. There's Eris, which is just a little bit smaller. Makemake, Haumea, all these objects are just a little bit smaller than Pluto, and there's a whole size distribution range in which there's many large objects out there and many, many more smaller objects out there. So then you always get the question, what do you call Pluto? And I always just like to say, a planet by any other name would have formed the same. So I don't want to get into the semantics of what you call it, what you don't call it. I'm interested as a scientist why Pluto is out there and what it can tell us about how the solar system formed, how the planets formed, and how the planets might have migrated and moved around. So let's get into some of the more dynamics now. So this is a plot showing the main asteroid belt. So Earth is here at 1 astronomical unit. Mars is here about 1.5. Jupiter's out here about 5. So here's the main asteroids. And there's groups of main belt asteroids. And what I want you to focus on is what we call Jupiter Trojans, which share an orbit with Jupiter, and these things called Hildas, which are about 4 astronomical units. They're on the outer part of the main asteroid belt. So if we look at this top down, this is what you see. So you see Jupiter moving here, and the Trojans are what we call a 1-to-1 residence with Jupiter. So they're 60 degrees ahead or behind Jupiter, and they go around the sun one time for every time Jupiter goes around the sun one time. And that's what we call one-to-one resonance. The Hildas, shown here in purple, are in a 3-to-2 Jupiter resonance. So that means the Hildas go around 3 times every time Jupiter goes around twice. And that gives you this kind of triangle-looking pattern. And the main point of the triangle pattern is these Hildas have kind of eccentric orbits. And so when they're at their most distant point in their orbit, out near Jupiter's orbit, they're on the opposite side of where Jupiter is. Oops. They're on the opposite side of Jupiter. So they come to their distant point here. And when they pass in front of Jupiter, they're at what we call their perihelion, their closest point to the sun. And so that means these objects, because they're in this resonance, are protected from ever getting close to Jupiter. And that keeps them stable for the age of the solar system. And by looking at the eccentricities of these objects, we can say that Jupiter probably moved inwards in order to get this kind of pattern that we see today. So that's the main asteroid belt. Let's move out to the Kuiper Belt and see what the Kuiper Belt can tell us about possible planet formation. So here's the Kyber Belt. Here's semi-major axis, or how far the object is from the sun. And here's its eccentricity, or how elongated the object is. We originally thought if you found these Kyber Belt objects, they'd all be kind of down here, low eccentricity objects just beyond Neptune. But that's not what we see. We see a very disturbed population. Here's Pluto, the P. It actually has somewhat of eccentricity, and it's in a 3-to-2 resonance with Neptune. So it's in one of these resonances. So what does that mean? Resonance. So I showed you the Hildas. Now I'll show you Pluto and how we think Pluto got there. We think Neptune originally formed closer in at 25 AU or so and moved outwards by some 5 AU astronomical units, and it pushed this original disk of smaller objects that never formed a planet into these resonances, into the 3-to-2, into what we call a 2-to-1. So it pumps up their eccentricities. So by looking at how eccentric these objects are, we can say something about how far Neptune moved. And Pluto is an interesting case. So here's a picture of Pluto. Pluto was at its perihelion, so its closest point to the sun in 1989. And this is what it looked like. Pluto was here. Pluto and Neptune was 90 degrees away. So Pluto actually crosses Neptune's orbit. And so that you would think that would make Pluto very unstable because Neptune is much more massive. But they're in this resonance. So what happens is some 200 years from now, Pluto will be back at perihelion, and Neptune will now be over here, 90 degrees on the other side of the sky. And then 200 years later, we'll be back to this. So every time Pluto is crossing Neptune's orbit, Neptune is not in that area. Neptune is 90 degrees away. And that keeps Pluto from ever getting close to Neptune, which allows Pluto to be stable over the age of the solar system. And that's what we call a 3-to-2 resonance. So there's a bunch of different resonances. Pluto's in the 3-to-2. There's the 1-to-1, 2-to-1, a bunch of other population resonances out there. So now I want to talk about a second group of objects, what we call the scattered objects. And Eris, the next largest object beyond Neptune, is in the scattered population. And these objects have large eccentricities, but they're all to the left of this dashed line. And this dashed line is simply where the object would come to perihelion near Neptune. If you're left of that, you come near Neptune. So this is a diagram showing that. So Eris, even though it's well beyond the Kyber Belt, it's out here at some 90 astronomical units, into the Neptune area, and actually gets very close to Neptune. And so we can explain this very elongated orbit of Eris because it likely interacted with Neptune in the past and got scattered outwards. So these scattered disk objects, and this is a simulation showing that. So this shows Jupiter, Saturn, Uranus, and Neptune. And if you have a disk of objects that never formed a planet, Neptune will interact with that disk and create that kind of arc that we see. So here's Neptune, and all the giant planets kind of scattering all these small bodies around. That moves out. These planets move out as they do that, and you can see it makes an arc of smaller objects out here. And all these objects have perihelia that come, the more eccentric the object is, the further out it is, but its perihelion comes in to where Neptune is. So what that means is all those objects in that arc, this is the arc, these are known objects, they all come near to where Neptune is. So we can explain all the objects in this arc because they have close interactions with Neptune. So that brings us to these two objects, Sedna and 2012 VP113, which are to the right of this line. These are two objects that we cannot easily explain with the currently known solar system. I like this plot better. This shows the perihelion distance, or how close an object gets to the sun, versus its eccentricity. And this really shows how Sedna and VP113 are in what we call this no man's land area. They have these very eccentric orbits, very elongated orbits, yet they don't interact with anything that we know of in the solar system. So somehow they have to get these elongated orbits, yet there's nothing that they interact with. And the interesting thing, so they're decoupled from the giant planet region, and they're close enough to the sun where outside forces are not a problem. So they're kind of in what we call the no man's land. Here's a plot just showing their orbits. 2012 VP113 here and Sedna here. One of the main things here is both these objects were discovered near their perihelion, near their closest approach to the sun. We would only be able to detect these objects for about 1% of their orbits. 99% of the time, when they're out here, they will be too faint for even our largest telescopes to see. So that means there's probably a large population of these objects out there, because we can only detect them for about 1% of their orbit. So the question is, where did those two objects come from? And the answer is likely when things in the solar system were quite different than they are now, because we cannot currently explain those objects with what we currently know about the solar system. So when the solar system was forming, there was a lot of different mechanisms happening that could have created those. And various different authors have come up with very different reasons. One is that they could be captured extrasolar objects, objects that came from some other star and got too close to our sun and got captured. But up until 2012, the belief was that they formed in the sun's birth cluster. And so that is when the sun was forming, there were a bunch of other stars forming right next to the sun. The sun formed in a cluster of other stars. And so outside forces were much stronger when our sun was forming than they are today, because there's all these other stars around. And so you could get the giant planets could scatter objects out, and then the outside forces, what we call the stellar tide from other stars, could lift Sedna and 2012 VP113 up into those decoupled orbits that we see. So that's the favorite theory about how those objects got formed. But the good thing is all these different scenarios, all these theories predict different size distributions, different inclinations, different eccentricities, different orbits for all these distant objects. So our main goal is to go find more of these. And what can they tell us? So here's the telescopes we are using. The Subaru telescope, the one I showed you at the beginning with all the snow, is in Hawaii. It's our we use in the North Subaru, which is 8 meters in size. It's the most powerful survey telescope in the world because it's so big and has a big camera. And then in the Southern Hemisphere, the second most powerful survey telescope in the world is the NSF Blanco 4-meter telescope down in Chile. And so we have both a southern and northern site, and we use these for discovery, and then we use other telescopes that don't have such big fields of view to recover the objects every month to a year or so. And so our survey started, and we found 2012 VP113 was one of the first very distant object that we found. And the interesting thing about it is its orbit is more tightly bound to the sun than Sedna is. So Sedna can go all the way out to about 1,000 AU, whereas VP113 doesn't go out to more than about 450 AU. So Sedna, its favored formation scenario was that it was from stellar tides, other stars in our sun's birth cluster pulling it out. But that argument becomes harder for 2012 VP113 because it's closer, more tightly bound to the sun. You need even stronger outside forces to pull it out into that orbit. So it's possible if we had a very dense stellar environment when we formed, but it makes it a little harder. So that's when we saw that, we had two objects, which is hard to say a lot with just two objects. So we started looking at these other things that we call extreme trans-Neptunian objects, objects that have similar eccentricities. Their perihelion distances are on the edge of the Kuiper Belt. They're further out. They get closer to the giant planets, so they have more interaction with the giant planets. So it's unknown if these objects are related to those objects or not. They could be, or they might not be. But we took 10 of these objects and these 2 objects. That gave us 12 objects to look at. And what we noticed is, for an orbit of an object, there's 6 parameters that define orbital object. There's the 3 kind of obvious ones, which are its inclination to the plane of the solar system, there's elongation or eccentricity, and then there's their symmetry axis, how far it is away. But there's also 3 angles to an orbit. And you don't really have to understand the angles too much, but one of them we call the argument of perihelion, which is a latitude angle. That's basically where its perihelion comes, its angle relative to the ecliptic plane or the plane of the solar system, relative to where it comes to perihelion at. So it's just kind of a latitude angle, how far above the ecliptic plane, the plane of the planets, the object comes to perihelion. That angle should be random for all the objects. So here's a simulation we ran over, this is 1 billion years. We simply put down the 8 major planets, and then we took 2012 VP113 and put it down in our solar system, and we ran it for 1 billion years. And its orbit, through this latitude argument of perihelion, it goes through all of these over a few 100 million year time scale or so. So it's just the angle precesses over the age of the solar system. And so the angle is fairly random. All the different objects in our solar system have the same, they precess, but they all precess at different rates. So even if you put down all the objects in the same exact angle, they would all precess at different rates, and they'd randomize over time. So this is what we expected to see. If you took the argument period in that latitude angle versus the major axis, we'd expect to see that, a kind of random distribution. But this is not what we saw. We saw this when we did that plot. And this is our 2014 paper, which shows that they oddly cluster at one type of angle. So the way that we explained that in 2014 was if you take this simulation, which had the 8 major planets and 2012 VP113, we simply added what we call Planet X. We took a super Earth-sized object, 5 Earth masses, put it into the very distant solar system, and ran the simulation again. And we got this. That angle is no longer cyclic. It's no longer random, goes through all the angles. It's now confined. So if you put a planet in the outer solar system, you can start confining the angles of the objects out there. And so that's one way you can explain these all having the similar latitudinal angle. So this was the situation in 2014 when we released our paper. We believed that there was a 2 to the 15 Earth mass object out there, 200 to 1500 AU orbit, so way out there, way beyond Pluto, 10 to 50 times further out than Pluto is. But in our paper, we also said there seems to be, so this is a latitude clustering. We also said there looks like there could be a longitude clustering as well, but more data needed to happen for that. And what that means is, here's a graph that I just made last night. It shows all the objects we discovered beyond the Kuiper Belt, beyond 60 AU. So this is, our survey has discovered 80% of these objects, and 20% of them also discovered by other surveys. So this is the current distribution of all objects discovered beyond the Kuiper Belt. And you can see it's fairly uniform. There's some gaps here where that's where the galactic plane is, and it's very hard for us to go into the galactic plane. Then I plotted where the location of what the high perihelion, the objects, these extreme objects with very high perihelia, the Sedna-like, VP113-like, this is where we discovered those objects. So kind of all over the place, more over here than over there, but we discovered some in all parts of the sky. And then I plotted, so this is where they currently are. If you plot where they will be at perihelion when they get closest approach to the sun, at what longitude will they be at, this is the plot you get. So even though they're discovered all over the place, they all come to perihelion and only on this side of the sky. They're not coming to perihelion on that side of the sky. All the other objects, the ones that interact with the planets much more, they're just randomly scattered everywhere. But these, the purple ones, the high perihelion objects, are clustered. So this is a longitudinal clustering as well as a latitudinal clustering. So in 2016, Badigan and Brown from Caltech took those 2 clusterings, and they did some sophisticated simulations that showed that if you put a far-out big planet onto an eccentric orbit, and you incline that orbit, it can confine these extreme objects into these longitudinal and latitudinal clusterings. So what that Caltech group did is they took us basically from this in 2014 to this in 2016. So they came up with the best orbit fit would be the planet X here on an elongated, it has an elongated orbit that's oppositely aligned to these extreme Kyber Belt objects. So that was early 2016. And then late 2016, we announced several more new discoveries from our survey, in particular 2014 SR346 and 2013 FT28. And the question is, how do those line up with our previous discoveries? And you go from this to this. So SR346 is very similar to these other extreme objects. And FT28 looks like it breaks that distribution, but in reality, it shows us that there's a second group of objects. So this group of objects we think are stable to the planet because the planet spends most of its time out here. And so it doesn't interact much with these objects because it comes through this area pretty quick, and these objects spend most of their time far out. Because that's the way dynamics work, is an object spends most of its time at its most distant part from the sun. So the planet spends most of the time over here. This object is actually aligned with the planet, and it never crosses the planet's orbit. You see, it's always interior. And when we run the simulations with this object, we find it precesses back and forth, but will never cross over the planet X location. So this is actually, we think there's two groups of objects. There's a aligned group and an anti-aligned group. And the area which is unstable is objects that would be in here, because they would be crossing the planet's orbit kind of close to where the planet spends most of its time. So just in October 2018, we announced a new object. These ugly names here, we just called it the Goblin because we found it around Halloween time. And so this is now the first object that is between these objects and these objects here. And this has a very eccentric orbit, and it has very high perihelion. So this is what the Goblin looks like. It continues showing the trends of the other objects. It's actually between where Sedna and VP113 are latitudinally wise. It has a much more elongated orbit than those, but it basically continues the longitudinal clustering trend that we saw. And so this object is very interesting because it was only just announced, pretty much just discovered. And we have this possible planet X orbit, which I show here in blue. And if you put the Goblin's orbit in, what you expect is if you ran this simulation, you would expect, again, all objects should precess. They should go, their angles should slowly move around the sun. So you expect this orbit to slowly precess and go all the way around, 360 degrees around the sun. But when we run the simulations with the planet, we don't see that. This is what we see. It's what we call libration. It's always staying anti-aligned with the planet. And this is an object that was just put in. We didn't do anything special with this planet orbit. This is planet X orbits that we already thought were good with the other objects. We find a new object, and it shows this stability here, which is very strongly showing that something interesting is probably happening out there. So in December 2018, we announced Far Out, shown here. And this is the most distant object ever observed in our solar system. And so it's shown here. So it's at 120 astronomical units. It's some 25 AU further than the last most distant known object. And here's a lot of the other discoveries that we've made out here. And this object we only just discovered a few months ago, so we're still observing it. We actually don't know its orbit. We just know it's far out. We don't know anything else. We don't know if it's actually interesting in terms of orbit or not. So that's going to take a year or two of observations to figure that out. But this is hot off the presses, far, far out. So yesterday it snowed, so I had nothing to do, so I went looking through some of our data. We have a bunch of data, and I actually found this object just last night. So this is a quick put together for this talk. You can actually see I didn't clean up the image. This is a real, basically raw image. You see all these bright streaks, and these are cosmic rays or high-energy particles that strike our detector and create noise. And they're annoying because they can mimic real objects at times. So you can see how dirty some of these images can get. But in this image is far, far out. which is, we believe, is now 140 AU, so 20 AU further than far out. And I don't know if anyone's found the object or not. I put it right in the center. I made it easy for you to see. But it's very faint. It's on the edge of our ability to detect it. This was just discovered in our data from last month. So we don't know anything about the orbit of this object. We just know it's far, far out. So we'll be following this object. I'll be going observing next week, and we hope to re-observe this object to get more information on it. And this image is also really beautiful because not only do you have a lot of stars, but you're actually in a galaxy, we call a galaxy cluster. So you see all these these are all galaxies here, and they cluster together at times, and this is in a galaxy cluster region. So it's a very beautiful image. So this is far, far out. It's off the plot here. It would be somewhere over here if we were able to plot that. And so just to finish up, this is what we think is happening in the outer solar system. We think there was a lot of chaos involved. So right now we see all the planets are on nice circular, calm orbits. And everything is stable. The Earth is stable. The giant planets are stable. But that probably wasn't true when the solar system was forming. We don't think the giant planets formed where we see them today. We think these planets all formed much closer to each other, and they kind of got knocked around. They pushed each other around. They're basically fighting for space, fighting for material, and they kind of push each other around to what we see today. And Planet X was likely, I like to call it the runt of the family. It likely was involved with all these other giant planets, and it got too close to one of these and got tossed outwards before it could grow really big. And so it's been tossed into the outer solar system where there's not enough material to grow. So it stunted its growth. It can't grow anymore. That's the most likely scenario for the Planet X if it exists out there. And Pluto was actually probably formed in this region and tossed outwards. Because of Pluto's eccentricity, its high inclination, we think it formed here, got tossed outwards, and then got captured into that resonance with Neptune. So the main takeaway that I think we've learned in the last 10 years or so is our solar system was a very chaotic place, a very stochastic environment. If this Planet X was tossed inwards instead of outwards, it would have destroyed the terrestrial planets as we know it. And Earth wouldn't be here as we know it, and we wouldn't be enjoying this great talk at this time. So I'll just say we have some ideas of the Planet X orbit, but it has a lot of possible orbits to it. But this is where we think it is across the sky. And the winter sky in the northern hemisphere, the Orion Eridanus area, is our best bet for where it is. We think that's where it's at most distance from the sun. That's where it should spend most of its time. So we're searching for it. We've covered about 25 to 30% of the premium sky location for it. So we have a lot more area to search. The three big questions about Planet X in terms of finding it are its diameter, its orbital distance, and its reflectivity. Those three things will tell us if we can actually find this object or not. If it's on the small end of its diameter, only a few Earth masses, if it's at the most distant part of its orbit and it has a very big orbit at thousands of AU, and it's as dark as coal, even our best telescopes probably wouldn't be able to find this object. But if it's in the middle range of these things, which is most likely, it's probably several Earth masses, it's probably medium distance, and it probably is a medium reflectivity. We should be able to find it with our large telescopes, with the telescopes that we're using. But those are big unknowns. We don't know those three things to any kind of degree. And I'll finish off the talk by saying we discovered 12 new Jupiter moons through this survey. We were surveying for outer solar system objects, which is the main part of the survey. But we put Jupiter near some of our fields last year and discovered new moons of Jupiter. And we now need to name those moons. So we set up a Twitter account, and you can now tweet what you think these new moons should be named. There's a web page here you can go to, carnegiescience.edu/name Jupiter's moons. But there's 5 of them to be named right now, and so you can decide what you think the best moon name is. Okay, thank you.
So we can take some questions. There's microphones on both sides if anybody wants to stand up and ask a question of Scott. It's over there.
Hi, if you think that Planet X got ejected from that secondary group and all of that group are gas giants, would you expect Planet X also to be a gas, if not giant, at least a gaseous planet?
Yeah, it's a good question, and that kind of falls into this these big unknowns here. If those gas giants are majorly hydrogen and helium, which you have to be pretty massive to hold on to hydrogen and helium. If you release hydrogen on the Earth, it kind of just escapes because Earth isn't massive enough. So if it's massive enough, if it's up near 10 Earth masses, it could hold on to hydrogen and helium. But the main question from your question is, does it have a significant atmosphere or not? And we don't know, completely unknown. And that will really depend on its reflectivity too. If it has significant cloud structure on it, it'll probably be more reflective if it doesn't have clouds. And so it's a big unknown. We don't know exactly where it formed, we don't know what it's made of, and we don't know how big it is. So completely unknown.
Over here.
Yeah, that was a great talk. Thank you. What actually is a planet? In other words, how does Pluto slip in and out of that definition? And what is the definition? And how do you know something that way out can even qualify as a planet? And I heard somewhere that there are more planets than there are stars. Have you?
Yeah, so every star, almost every star seems to have planets. So almost every star has multiple planets. So that would mean there's more planets than stars.
Okay.
And in terms of how do you define a planet, that's kind of it's kind of semantics to some degree. I always like to associate it with continents here on Earth. A lot of us grow up, especially here in the United States, we learn there's 7 continents. But if you grow up in Europe, you grow up in South America, sometimes you learn that there's 5 or 6 continents. Some people think North America, South America is one continent. Some people think Greenland's a continent, Eurasia is a continent. So the word continent is a big landmass, very simple idea, right? But when you're trying to define it, when you get down to the borderline cases, it's hard to get it. So that's what Pluto just happens to be right out of the borderline case. It's big enough that it's spherical in size, which is the 3 main definitions of the planet. You need to be spherical in size. So you have to have enough gravity to overcome material strength to make you spherical in size. And you have to be orbiting the sun. And the third one, part of the definition, which is a little bit more hard to exactly understand, is that you need to be the dominant object in your environment. So you need to clear out the area of other small objects. So the reason Pluto fails in some people's regard is that there's a bunch of other objects on very similar orbits as Pluto. And so Pluto doesn't necessarily stand out. It's the biggest object, but it's not that much bigger than the next biggest object.
Thank you.
Over here.
Could you say something more about refining the orbit of these objects that you've discovered, how long it takes and how much it changes over time?
Yeah, so you saw that the Goblin, actually, we first saw that in 2015. It took us 3 years of observations to get the orbit of that object down, because it actually depends on the orbit. The object's orbit is fairly small. Its semi-air axis is small, 100 astronomical units or so. We can get that orbit pretty precisely within a year of observations. But the Goblin, let's see if I show that here. It has this very elongated orbit. It's huge. This is a 35,000-year orbit. It takes 35,000 years to go around the sun once. So, and we've been observing it for 3 years. So it takes a long time to get a big orbit like this compared to an object that has a smaller orbit like that.
Over here.
Thank you. Perhaps a naive question, but where does Planet X sit as a theory right now, as an explanation for the orbits of these very distant dwarf planets? Is it considered like far and away the best explanation for what we're looking at, or are there other theories?
Yeah, it's a good question. It's definitely not naive because that's what astronomers are discussing now, and it kind of depends on who you talk to a little bit, because of low number statistics, we only have a handful of these objects. So the main goal of our survey is not necessarily to find the planet. We'd love to find the planet, but we need to triple the population of small objects we have out there. So we've been covering the whole sky as much as possible. We've covered about 25–30% of it to find the smaller objects that can tell us about this bigger object. But it depends on who you talk to. I always like to say the Planet X is more likely than not. I personally think it's about 80% likely. But again, it depends on who you talk to. If you look at the numbers, I think most people come up to reasonably saying it's 30% likely to 80% likely. And I think it's not a slam dunk, it's not obviously real, and we need to find more of these small objects to really nail down exactly what's going on out there. What are the other theories? Well, the clustering we see could not be real. It could be just biases in our observations. We find certain types of orbits and not other types of orbits. The thing is, if the clustering is real, which it appears to be real, as we find more and more of these objects, the clustering seems to be more and more real. The best explanation that we can come up with is that there's a planet out there. There's no other explanation that really covers everything that we're seeing out there except for the planet theory. But there's also probably something we might not have thought of. So there's always the situation where the clustering is real, but we just haven't thought of a good mechanism for it yet.
What are some of the factors which help you make certain objects distinct from each other to help you not label them twice?
To not observe them twice? Is that? Well, in terms of observations, we only look at areas of sky that no one else has looked at to this depth. So there's a good catalog of objects out there run by something called the Minor Planet Center. And so when we find an object, we can then look to see if it's known or not. And so that allows us to know if something's real or not. But most of our objects are very faint, and no one else has gone to the depths that we're going to in these areas of the sky. So almost everything we find is new.
Go ahead. Yeah.
When you detect these objects, you have a point of light, and you can see how it moves. How do you disentangle reflectivity from diameter from just that information? Yeah,
so actually most of the objects that we find, we don't know how big they are. They could either be big and as dark as coal, or they could be small and as bright as snow. So we're most interested in just barely detecting these objects. As you saw with that far out, it was on the edge of detection. That was very faint. And so what you actually need to actually find out the compositions of these objects or what they're made of, you'll need the next generation telescopes, because these things are just barely seen by us. So Carnegie is actually involved with the giant Magellan Telescope. It's going to be the largest telescope in the world. The mirrors are going to be as big as basically a basketball court. So this thing is going to be massive. And we're building it down in Chile. And it will be able to look at these objects that we can just barely detect now. Something like the giant Magellan Telescope will be able to tell us about what it's made of and things like that.
Thank you.
Last two questions over here.
Okay, I'll go ahead and address the elephant in the room with my question. I think because you're being very modest, I think we all want to know, why don't you just name one of those newly discovered moons after yourself? And two, follow-up question, if I can get on Twitter and rally the troops and make that happen for you with a campaign, will you go ahead and name one of the other moons after me?
So what's your name?
Mike, and a very unique last name, it might work, Hamburger.
Okay.
Hamburger 1.3-H.
Okay, I'll look it up. Thanks.
At the very cold temperatures you have out there, the edge of the solar system, how small could a body be and still hold on to its hydrogen?
It'd have to be very, very big to hold it. Hydrogen, I mean, I don't know all those dynamics, because when you get out there, it gets colder, so the hydrogen moves slower. But you'd have to be several Earth masses to hold on to any kind of hydrogen out there.
Even at those cold temperatures?
Yeah.
Great. Thank you very much for coming tonight. Before you go, I'd like to point out that the next Capital Science Lecture is March 5th. It's given by Martine Rothblatt. So we hope to see you then, hopefully with better weather, too.